Hi, everyone. We're on lesson 27 on critical values. These are the numbers that tell us how the confidence levels, like 95%, affect a confidence interval. The critical values, or CVs, as I'll abbreviate them, come from distributions such as the Z, a T, or a chi-square distribution. And in lesson 27, we're going to be working a lot with notation. So you're going to learn to be familiar with various notations like these. So we're going to use two critical values, or CVs, to construct a 1 minus alpha confidence interval, or CI, for a population parameter such as a mean mu, a population mean mu. Now remember, what makes a confidence interval a confidence interval? Well, an interval estimate is a range of values, like your TA saying, I think that the mean test score in the lecture class is somewhere between 70 points and 78 points. And if you ask your TA, Igor, how confident, how sure he is that the mean will be between 70 points and 78 points, and if Igor says, oh, I'm 95% sure, or 95% confident based on my statistics, then, well, based on statistics, hopefully it's not too personal, but based on Igor's knowledge of statistics, there's a 95% chance that the true population mean is somewhere between 70 points and 78 points. So if you attach a confidence level like 95%, 95% is standard, although we will use different ones as well in this class. If 95% is the attached confidence level, all right, then we have a 95% confidence interval. So 1 minus alpha would then be the decimal equivalent, 0.95. So 1 minus alpha is the confidence level in decimal form. And the standard confidence level is 0.95 in decimal form. All right, now if we're using a Z distribution, then we denote, I'll move this up, then we denote these critical values, which again are the key numbers from the distribution, like Z, that we're going to use to construct these confidence intervals. These critical values are going to be denoted by plus or minus Z sub alpha over 2, or half alpha. Wow, why is that? A picture would help. And bear in mind, you don't have to worry so much about this notation on homework or exams. Well, you'll see it. I mean, you will see this in formulas. I want to explain why this notation looks the way it does. And by the way, we will see similar notations for T distributions, but for chi-square distributions, remember, chi-square values are never negative, so we're not going to have the plus minus symbol for chi-square critical values. Anyway, let's explain this notation. Why do we denote the critical values from a Z distribution as plus or minus Z sub, meaning subscript, alpha over 2, or half alpha? All right. It comes down to this picture. All right. So we have two critical values. Let me extend the window a bit. All right. So we have two critical values from the Z distribution that we're going to use to develop our confidence interval for mu, a population mean. Okay. So we have two critical values. Z sub alpha over 2, which is going to be a positive value, and its opposite over here. These are going to be the two critical values, and as you might suspect, they're going to be symmetric about 0, the mean of the Z distribution. Because remember, the sample mean is going to be at the center of our confidence interval, and this is a reflection of that symmetry. Okay. Now, once again, we're looking for a certain confidence level. Let's say 0.95, our standard, right? So if 0.95 is our confidence level in decimal form, 1 minus alpha, our confidence level, is 0.95. Well, then what's the complement? The complement of 1 minus alpha is just alpha. These are complementary probabilities because they add up to 1. Now you might be wondering, why are we labeling the confidence level this 1 minus alpha jazz? Because alpha here, which is going to be the total tail probability, the alpha here is going to have literally significance in the last part of our class. In fact, alpha is going to be called the significance level in a hypothesis test. Anyway, if 0.95 is the confidence level, if that's 1 minus alpha, then what's the complement? What's the value for alpha? 0.95 plus what will get us 1? 0.05. In other words, if we have 95% in this white region in the middle, we're going to have 5% in this, we're going to have 5% total in the two blue regions in the tails. All right. Now you see here two tails. This total tail probability of alpha is going to be split in two. And that's why we have half alpha, or alpha over 2, over here, representing this area or probability in here, in this left blue region. And the same by symmetry, half alpha, or alpha over 2, which represents the area in blue in this right tail over here. We have symmetry between the two tails, corresponding to the fact that we have symmetry between these two critical values. Now later on, when we use t-distributions, we're going to use a similar notation, except that instead of z's, we're going to use t's. But it's going to be really the exact same picture, except that we're going to replace z's with t's. The chi-square pictures, however, will be different, okay? Because the curves there look different, and there's a brick wall at 0. And we'll discuss those later on. Okay. So what if we have a 95% confidence level? Then you might be able to memorize these. Many stat students actually do. What are the critical values that correspond to a 95% confidence level or confidence interval when a z-distribution is involved? So what are these critical values that will trap 95% or 0.95 probability mass in the middle and a total of 5%, 0.05, symmetrically in the two tails? Remember, it's 5% or 0.05 total in the two tails. For each individual tail probability, you cut in half. So it's 2.5% or 0.025 in the left tail and 0.025 in the right tail. Okay. Now, if you remember the empirical rule, and I hope you do, the 68, 95, 99.7% empirical rule, we expect that with really approximately normal data, that about 95% will lie within 2 standard deviations of the mean. So a clever student with a good memory might think, hey, the critical value here should be about +2, and the critical value here would be about -2. And that student would do a very good job. However, we can refine the estimate a bit more because this rule was not super accurate. Instead of 2 and -2, to 2 decimal places, we should use +1.96 as our positive critical value. So this thing here, the 1.96, is our z sub alpha over 2 critical value. And its opposite, -1.96, will be the opposite of z sub alpha over 2. So these are the 2 critical values if you're drawing from a z-distribution, and if you're looking for a 95% confidence level for your 95% confidence interval. Okay, what about 90%, which is also one of the more common confidence levels? For a 90% confidence level for a z-distribution, again, some students memorize these critical values. Here it's going to be here the critical values will be about plus or minus 1.645. Positive 1.645 and negative 1.645. It makes sense these are a bit closer to 0 because we're trapping less probability, only 90% or 0.90 in the middle. Remember for 95%, when we were trapping 95% in this white space in the middle, the CVs were out at positive and -2 almost, really about plus or minus 1.96. If we're trapping less probability in this white space in the middle, then these values would be closer to 0. They're more closed in, about plus or minus 1.645. And by the way, we often go to 3 decimal places because, in fact, it really is almost smack dab in between plus or minus 1.64 and 1.65. So the 3 decimal places is pretty accurate. All right, so these are the critical values that trap 90% or 0.90 in the middle. That means we have alpha or 10% total remaining for the 2 tails. And we always split the tail probability symmetrically between these 2 tails. Even for a chi-square, we're going to do that. So the 10% gets split up into 5% for the left tail, 5% for the right tail, symmetrically. And again, that corresponds to the fact that the CVs are opposites. All right. For a 99% confidence level, now as opposed to 95%, we're really going to spread the CVs out. We're going to trap a lot of white space in the middle. We go outward. We go outward to, look at this, positive 2.58 and negative 2.58. And these CVs will trap 99% or 0.99 in the middle. 99% in the middle, so that means 1% total in the 2 tails. That leaves a measly 0.5%, 0.005 in this tiny left tail over here and in this tiny right tail over here. Again, we use symmetry. We're breaking this in half, each half for each of these 2 tails. Now, stat students are not required to memorize these critical values, but as you do your homework, you tend to see these values a lot. Because if I give you a confidence level, and if you know you're dealing with a z-distribution, then there are 2 particular critical values you're going to deal with. And for the common confidence levels, like 95%, 90%, and 99%, which are the 3 most common confidence levels, many experienced stat students actually remember these critical values for a z-distribution. Later on, I'll show you how we can deal with critical values for t-distributions and chi-square distributions, but you're not as likely to remember those critical values. Why not? Because how many t-distributions and chi-square distributions are there? There are infinitely many t-distributions and infinitely many chi-square distributions. It would be a total waste of time to even try to memorize the special critical values in those cases, even for these special confidence levels. There's just too many values. At least for the z, for the single sole solitary standard normal z distribution, well, over time, you tend to memorize these things. Especially since, for example, for 95%, you have about plus or minus 2 here. These are pretty easy to remember. All right. Next up, we're going to talk about, well, how to use software to find critical values and how we actually construct confidence intervals. And we may as well start with software. We can look at things like Excel, for example. Next time.